Alright, we're back. I'm going to do another lecture here on some Houdini Wrangles and some Vex. If you watched the first video, I mentioned something about using a solver sop to build up values over time. So in this lecture, I'm going to show you how you actually can do that. It's pretty simple. You can open up a fresh session of Houdini. We don't need to reuse anything that we covered in the first lecture. We're just going to rebuild everything now. Once you have Houdini open, just hit Tab and type in Grid. Drop a grid node down and dive in by double clicking. We can leave it at the default settings for now. And let's just jump right into this. We're gonna move this up here, hit tab, type solver. We'll drop down a solver sop and plug it into that first input. Let's enable the display flag here, so we're gonna see the output of this solver sop. We can leave everything up here at default for now. We shouldn't need any more cache memory than this. Let's dive in by double clicking again. Now, if you've never looked inside a solver sop, it can be a little confusing. There's all these nodes over here in this prev frame. I'm going to be honest with you, every time I've used a solver sop, I don't think I have used anything except input 1 and prev frame. All these other ones, I don't think I have ever actually needed any of this stuff in a setup that I've done. Maybe once or twice, but if I ever have used these, I'm not remembering it right now. So you can forget about all this stuff. Let's just focus on these two right here. So what do we have here? Input 1. All this node is doing is bringing our input 1 geometry into our solver sop. That means this right here. Okay, all it's doing is bringing in our grid. And then prev frame. This is where the magic of the solver sop happens. It basically allows you to look at data on the previous frame. So that's how we can actually start to build up values over time and use them to our advantage. So let me show you how to do it because it's much easier to understand it if you actually see an example. Hit tab, and we're going to use our Wrangle node again. We're going to use Wrangles a lot since this is all about Wrangles. Plug our input 1 into our first input. Plug our previous frame into our second input, and let's enable this one here so we can see the display and actually wire the output of this attribute Wrangle into our out node. So let's create a variable here. If you recall on our previous example, I think we had 99 points for this default setup. It looks like we have the same here. You can see down in this corner. It might be hard for you to see it on your screen, but this is 0.99. So let's go in here and we're going to create something almost identical to what we've already done. We'll create an integer variable here. We'll call it, how about pnum? And that's going to equal fit01 and then rand, and let's use our frame, and then now let's make it fit between 0 and 99. And now let's look up here at our geometry spreadsheet. Geometry spreadsheet is great because it will allow you to see your actual attributes that you're creating on a per point level. Since we're in point mode, you could switch over if we are working in primitives. This is your primitives tab, vertex tabs, and our points. If you've never used the geometry spreadsheet, I suggest to start using it. It's fantastic, actually. So we can see we have a tiny little green squiggly line under this equals, and we have a little exclamation point. It's complaining about something. It's going to be super minor. It's just complaining about an integer format here. You can see right here, implicit cast from float to int. Use explicit cast instead. Now, if you don't do anything, it won't make any bit of difference. It won't make the code malfunction, but a lot of people don't like having errors or what appear to be errors. This is more of a warning. It's not an actual error. We can fix this by just doing a typecast. Encapsulate all of this in our int, and if we click off of here, you'll see now the squiggly line is gone and our little exclamation point is gone. This is all rehashed from our last video. You should be very familiar with this if you watched the original video on my lecture on Wrangles. Now let's go and say if ptnum is equal to our pnum, get our little curly braces, and we can say at p.y plus equals our, let's just say 1.5. Now let me explain exactly what's going on here in case you're curious about what this pnum means. This should look very familiar to what we've already covered. All we're doing is creating a random number that's based off of our frame, so that as we hit play and this changes, you can see we have our pnum changes. It's the exact same number being generated for every single point. That's fine, because all we're doing is basically telling it an explicit point number, and that will be the point that then moves up in Y. Okay, so if that doesn't make any sense, we're fitting this range to 0 to 99 because we have 100 points and they all start at 0. Then we're just going to say this little if conditional. If our point number is equal to pnum, move it up in Y. Right now, on frame 22, that random number that's getting generated by this line of code right here is being calculated to number 16. So our point number 16 is going to be the point that moves up. We can go over to our scene view and we can look. You can see point 16, that is our point. It's going to change every single frame. Now this is just like what we had before, but as you can see, it's not persistent, it's not staying up. We wanted it to stay up. That's the whole point of using our solver sop. So there's a little bit of a trick you need to do for that. This is where our secondary input right here, our prev frame, comes in handy. Let's just create a new line here, and we're going to make a vector, and let's call it just pose, and we'll make it equals to. Now we're going to use the point function, so type point. I'm pretty sure we already covered this in the previous lecture, but if you do not recognize this, I'll go over it very briefly. All this does is allow us to get point data off of any point we want. It's going to ask, as it's showing here, the first thing it looks for is geometry. That's going to be 1. And the reason is because we want our second input. And our second input actually has an index of 1 because all the inputs are indexed from 0. It then wants our string attribute name, which is going to be just p for our position, and then the point number, and that's just going to be ptnum because we want to do it on every single point. So we just type in 1, comma, quotation mark here, p, quotation mark, comma, and we just do at ptnum. Now nothing's going to happen because we've just gathered this data. We haven't applied it to anything. But now we could then say, again, at p plus equals pose. Let's do it though here just on the dot y plus equals dot y. Now let's rewind. And if we hit play, it still doesn't look like it works, but there's usually a trick here with these solver sops. A lot of times when you're inside of them, they do not display correctly the result of their own node. So you got to go back up to grid here. Let's see why it's complaining. It's probably another useless complaint there. Solver sop cooked. Yeah. You can hit reset simulation. And now you see it goes away. And we have our point up here. Hit play now. And you can see, look at that. It's climbing and climbing up. And you can see it stays, it persists. Let's hit stop. Let's enable our little clock face here because you know that's going to give us our real-time playback, so it'll slow it down to 24 frames a second. So now you can see you can actually build up those values over time, where that plus equals now actually legitimately is plus equaling every frame, unlike before where it just would pop up and then go back down to 0. Now we can actually persist these values and build up these values over time. Let's disable our point number here so we get a little cleaner view. Now let me show you another trick though. You might not like this. You might want to have it slowly receding after it goes up. So it's very simple to do. We can just go into our solver sop and we can just add another line of code underneath this and just do at p times equals and now a fractional value like say 0.85. And now again if we hit play in here, we can't really see the correct output. There is a way you can fix this. If you go back up here to grid, go to this little pin and just enable it. Now we're pinning this view, which means no matter where we go in Houdini, this is the level of the view we're going to see. And by level, I mean at this level of geometry, we're going to always see this node in this state. Let's hit reset simulation and dive in. Now you hit play and now you see they do rise up, but then they slowly start to fall down over time. Now, if that's too much falling down, you can change that. You can say 0.95. Now hit play. And you can see they slowly fall down. I think I've shown this setup before using this times equals and a sub 1 value, a fractional value, to reduce these values over time. Probably not in this free lecture series, so this might be new for some people that haven't seen it before. Now, so this is pretty cool. You know, now we have the ability to build up these values over time, but let's see if we went up here. Let's copy this, Alt and left drag it. Let's visualize it, and now let's just say we had a much higher resolution grid. Okay. And let's plug it in. And let's see what happens. Rewind, hit play. Well, that doesn't look all that good. It only occurs down basically one row of our faces here, and that's because our point count now is much, much higher. If we enable our points, look at how many there are now. Let's see if we can even find the edge. 99, that's probably not it. Let's go over here. Look at that. We have 9,999 points. So we have way more points, and with this type of setup right now, you would have to go in here and change this manually, but I don't want to do that, and nobody should want to do that. We can always make it automated with Houdini. Let's Alt and left drag this over so we get a copy of it. Now we can go up here, and let's use our endpoints function. So create an I at, and we'll just call it num points equals n points. Now n points, spell it correctly, n points is a function returns the number of points in the input or geometry file. So once again, it is asking for a geometry, and we're going to want to use our 0 input. And now we can actually confirm that this is correct by going up to our geometry spreadsheet. And if you look, n points, now it tells us we have 10,000 points, which is correct. You saw that it went up to 9999, which actually means 10,000 points because the first point is always 0. So now you can just copy this. You don't need to copy the I if you don't want to. You just need that at symbol and just replace this. And now if we hit play, okay, stop, go back. We have to actually wire it in or else we're not going to be using it. Now if we hit play, you'll see that it occurs all over the grid here. And then it wouldn't matter. No matter what you do, you could reduce this and it will just automatically know exactly the number of points that it needs to use. You can confirm that again by going in here and checking it out. Num points, now it knows it's 2,500 total. So this is a very good function here that you can use to help set up automated rigs. So now let's see what we could do here. Well, it's pretty sporadic here. You could actually do a little trick here on the solver sop itself and say substeps. Let's increase that to something like 15. Now let's hit play. Now you see it happens a lot faster and a lot more of them are triggering here. When you have a grid like this, it might actually be more interesting to not have these things fall down at all. You can just remove this line. Nope, not that line. This line down here, we can just remove that. Go back up here. And now you'll just see what happens. They just get spiky and keep going and going, and they'll just keep adding up on themselves. Now you could also then do some post smoothing on this. You could drop down just a smooth. Plug it in. And you can see what you get. It smooths it out a little bit. Looks a little nicer. You could change some of these attributes around. And now you can see you can fix those edges there. So that's pretty cool. Just a simple trick you can use in a solver sop to have values build up over time. This is used actually a lot. If you've ever seen any of my other lectures that use the color transfer and a solver sop trick where you build up color over time, I'll show you that later on and show you how useful that is for rigs. That's probably the foundation of 50% of the rigs I make, maybe even more. It's really that useful. Now, like usual, I like to show how to do things in more than one way, so if you wanted to do something almost, let's say similar to this, it's not exactly the same thing, but I'll show you a non-wrangle way. You could just drop down a subdivide. So we're going to get a lot more points here, a lot more faces. Increase that depth. Drop down a VOP, so just type VOP and pick an attribute VOP. Plug into that first input and dive in. Now this has nothing to do with Wrangles, so I probably shouldn't even be showing it to you in this lecture, but I'll just show you real quick. You can drop down a turbulence noise, plug the P into the pose, and let's drop down a set vector component. And we're going to plug P into the vec. Now what this is going to help us do, we're actually just going to replace the Y component with the output of this noise. So we can plug in this noise into fval, and you say 3D vector is correct. Component 1 would be the x-axis, which we don't want. We want component 2, that's going to be the Y, the up, and then plug that into P. And you'll see what happens. It just displaces this grid up in the Y, which is nice. But let's modify this a little bit. Let's drop down a smooth node in here and plug this noise into our min and plug the val into the fval. And now we gotta do a little adjustment here. Let's change this to 0. Or let's just go close to 0. Now you can see you get these flat pockets, so you've clipped off some of that noise. We could then increase our amplitude. Let's do some changes over here. So you get something similar to what we were seeing over on the other thing, you know. Now, there's no animation to this, but you could then promote this offset if you click this little sprocket here and say promote parameter and go on up here. We can then do things like offset it. We can offset it in X. So you could do $F times like 0.1, and now that's just going to make it slowly drift through the X-axis here. Remember, if you want to do any type of animation, you can't really do that in the VOP. You have to go up to the geometry level, and you can promote those parameters up here, and then you can do stuff like this, but this isn't really Wrangle related, so I'm not going to really go in depth to this. I just want to show you there's an alternate way of getting a similar look. Now, this is kind of cool and all, but, you know, working on a flat grid isn't always all that interesting or exciting, so let's actually make this much more interesting by doing this on a sphere. So let's drop down a sphere. You can pick that first one, polygons. We'll zoom in a little bit here. And let's change this to polygons. Up this frequency a little bit here. Let's drop down a normal node. So hit tab normal. Wire it in. All this is going to do is give us surface normals, which you can see right here. Actually, point normals. Let me state that correctly here. Let's change this also to point so that that point normal is on the point normal and not the vertex. Just will make it easier for us to access it later in a Wrangle. And you can see all it is a line that comes off of the point. A lot of people refer to them as toothpicks. They kind of look like them. Let's also drop down a color node now and wire that in. And we're going to set it just to black. Now let's also drop down a Wrangle. Attribute Wrangle will do it. And we're going to basically redo exactly what we did over in the solver sop. So we can say I at n points equals n points. Sometimes you wouldn't want to name it the same name as your function, but you know what, it doesn't matter because we're just doing this as an example. Type 0 because we want that incoming geometry. We can confirm this is doing what it needs to do, 362 points. Now let's create an I at, and we'll just do like pnum equals, and we'll do our fit 01 and rand, and we'll do at frame. And we're going to do 0, and we know we want it to end at the end points. Again, nothing happens yet. We've only just created this value, and again, we have our little int problem, so if you want to fix that, you can do this trick of encapsulation and typecast it to an int, and now that goes away. And now we will do if ptnum is equal to pnum curly brace and curly brace. And let's do something a little different here. We're going to use color this time. At cd dot x equals 1. Now you can see down here, a little red point occurred. Let's back this up. You can see what's happening now. We're going to get a red point at all different times over the frame range here because that's exactly what we want. That's how we set it up. It's just going to randomly color a point red, and that red's going to come in handy later on. None of this should be too confusing to you, especially if you've watched my previous lecture. This is all very basic. If you skipped over that one and you don't know what this means, this is just the double equals. That's a comparison. We're not trying to make this ptnum equal to the pnum. We're just testing for a comparison. That's what this if statement is. It's a conditional. And if the left is equal to what is on the right, then we're going to enter in and run this block of code. That's why we get this little red point changing every frame. Because every time we change a frame, we get a new random number here for this pnum, and then it's between 0 and the number of points we have. So it's always just going to be picking some random number on our sphere. It's very simple, actually. So now let's drop down our solver sop. This is where the magic's going to happen. Plug into that first input. Dive in. Drag this input 1 over here because it's the only one we care about. This one and this one. We don't want to bother with any of these. Hit tab and drop down a wrangle. Plug this input 1 into input 1 and the previous frame into the second input. And then plug its output into out. Now we're going to do the same thing where we're going to say at CD and we want to do plus equals. And we're going to do point. And we want 1 because we want to look at the value of this from the previous frame. And we just do CD and at ptnum because you wanted to do it on every single point. Now you see, might have been hard for you to see on video, but when I clicked off of this, it actually got brighter in red value. And if you hit play, you'll see that now they just persist. We get red splotches all over this thing, which in itself can be used for creating a lot of different effects. But we do want this to go down over time. We want this red to get sucked out of there, so it's very easy to do, as we've already seen. We just times equals a fractional value. We can do, say, 0.8. And now you see you get these little almost raindrop effects, which, again, you can use that for a raindrop effect. I can show you that later, actually, if you want. So let's get out of here, and we'll go back up to our geometry level. Now we're going to use one more wrangle out here, attribute wrangle, plug into that first input, and let's type in if at cd.x is greater than 0, enter a block of code, and what's going to happen? So any point that has a value greater than 0 for the red channel is going to then have this code run on it. So, as you can see, this will be the point that gets executed first. And now we want to use that normal value we created because look, if we can move it along the normal, it will always be going away from the surface of this sphere and it'll look cool. If we used our old setup and just modified the p.y, that would not work on a sphere. That would just move every point up and y no matter where they were. So on the top that would work because it would go straight up. But on the end over here, the point would also go straight up. It would not look good at all. We want it to go off and away from this spherical surface. So we can just do at p plus equals. And we can do n times cd.x. And now it's probably going to be very, very strong. And look at that. We get these gigantic spikes. Let's disable our normal visibility now. And let's scrub through it. You can see how they spike out like crazy and then they recede, which is cool, but that might be a little too long for our liking, so you can always just multiply this whole thing by a fractional value. Let's just try 0.1. That might be a little too small. Just depends on what you're going for. I'd like them a little bit bigger, so let's just go like this, 0.25. And then we can always drop down a color node, plug in. Now we can see it much better. And then even on top of this, we could do something like a smooth node or a subdivide. So let's drop down subdivide. Come on now. And we'll plug it in. visualize it, increase this, makes it a little smoother. So we'll hit play there. And that's pretty cool. Very weird and interesting surface. But think about this thing as something that maybe gets shaded like a cell shader, or, you know, and by a cell shader, I don't mean like a toon cell shader. I mean like a microscopic cell shader, something like with a Fresnel edge where it gets transparent in the center and hard on the edge. You could make some subatomic particles. You could do some really cool looking things. And this is one way you could do it. And just to show you an example, if you really wanted to simplify this code from this, I just copied this over. You could actually remove this if statement and it'll still function the same way, as you can see. Now the reason why this occurs is because when the CD is 0, when CDX is 0, it won't actually add anything to this position. Why? Because if it's 0, it doesn't matter what our n is, it doesn't matter that we have 0.25, you're going to multiply all of this by a value of 0, and so the value will be 0. So you technically don't have to do this if structure. I usually do that though because it's usually not this simple, but for this simple example, you could get away with removing the if and just using it like this. And as you can see, it still does exactly what we want it to do. So that's all I'm going to go over in this quick lecture. It's just a quick introduction to show you how to build up those values using solver sops. It's actually quite easy. It shouldn't cause too much confusion. If you do have any confusion, just go back and look at it again. It should make sense once you look at it a little more. We're really not doing much of anything difficult. The only thing that can be confusing a lot of times is this idea of this previous frame and the fact that, you know, we just use a point function to just read in this value of this one input. You know, it's the second input, but it's 1 because they start at 0. And that just allows you to see what the value of any attribute was on a point in the previous frame, and then you can add it to it, and that's how you build up your values over time. Now, this might seem very basic, and it is, but, you know, this is the building blocks of some very powerful things. I'll give you a little preview of what's going to be an upcoming video right here. I use this trick constantly for doing these big shockwave type setups, and, you know, there's points that emit, and these points then would be, say, perfect for the emission of stuff like fluids or pyrosims or whatever you want. More particles could be emitted, and debris, rigid bodies could be emitted, all different things could be done. But this is the building blocks of how you start setting up something like this that's more advanced and something that you would see in a feature film or a television show or something like that. I've done too many shockwaves in my career as a post-production artist, I'll put it that way. So that's all we're going to look at here. I hope you enjoyed this video. Make sure you like and subscribe if you liked what you saw. It helps that algorithm be happy. Stay tuned and keep looking out for more lectures, because there's more that will be coming. And if you get a chance, go check out my Ko-Fi page, ko-fi.com/EblingFX. You can see exclusive content over there, longer tutorials that are on more advanced topics. You do have to subscribe for that, and it's a small fee, but it's well worth it if you want to learn this software. And with that being said, I'm going to shut this video down, and I will see you in the next one.